Okay. So, yeah.
Alrighty, so when we left our daring heroes, to begin with convolutional neural networks for image processing, first an image is fed into the first layer of the neural network, whereupon each node has a series of kernels that will work over the image. Each kernel being an n by n grid that does matrix operations on each pixel to try and find similarities. So that in the end you wind up with the output being an image that's going to be, one second, let me see if I can remember the equation. What was the equation for the output image?
The size?
Yes.
And minus k plus 1.
Okay, minus k plus 1. So n being the dimensions of the original image, minus k, so the dimensions of the kernel that scrolls across, plus 1 pixels. And it'll be easier once. A little bit to show this kernel process. Are you familiar with how a kernel will walk across an image to try and find latency? Okay.
What's the definition of a kernel?
The kernel is just a matrix object that the neuron works across an image, transforming it to try and find particular features. Okay. A good the example from that's on the screen right now is a kernel that's trying to detect a transition from dark to gray to white. So you have on the left, you have the matrix that's the image itself, like tensor board. You then have the kernel next to it, which is provided by the neuron, that will operate on each segment as a grid. So first, if you'll notice that there's the highlighted 3x3 region on the left. The kernel will first walk across that to provide the output pixel. And if you go over to the far right, you see the first operation from that kernel operating on the first pixel. Then it's going to go down 1. And of course, you'll see it'll be 0 because essentially you're for each pixel on the left-hand side, you've got, one moment.
Okay, maybe I should make it more structured instead of throwing this on you completely randomly. My apologies for that.
It's all right. It's a little bit fun even.
It showed me what's going to be expected in the future. So if you think, let's say you were a witness in a robbery, and it's a bank robbery, and now you want to help the police to find the suspect. So you saw that person's face. So how can you help?
You can pass along information on unique features, any particular scar, color of hair, skin, pupils, whether they had any piercings or tattoos, how many teeth they had or didn't have.
Right. So a visual description. What if the police had an artist who could work with you and draw that description? Would that be helpful?
Probably.
And if they drew that description and that was broadcasted on TV, what will the general people do when they look at that, what the artist drew?
I looked at it and I said, wow, that looks just like Stan. Like, what about my work? And then Charlie came by and said, hey, did you see Stan in the newspaper today? It's like, no, I can't be them.
So,
It's true.
so essentially, that what the police artist drew was sort of a template that you were able to see and you knew what Stan looked like and you were able to match
Dead ringers.
Right.
Make the eyebrows bushier, no, the face is thinner, and they zoom in on.
that. Right. So when you sit down with a police artist, what does the artist first do?
Go for the outline of the face.
Very good. And once we have the outline of the face, what's next?
The nose is very prominent in the eyes, eyebrows, hairline.
Very good. And once you have those things, then what do you do?
Mouth, ears,
Right.
hair.
And with all that, what does it look like?
Kindergartner's rendition of a picture, and then you have to change it and make it look like.
So that's exactly what a neural network does. At the end of it, it's trying to learn some sort of a template. Let's say you're building a neural network to categorize between male and female faces. There are a series of layers in your convolutional neural network. And the initial layers, it's learning the edges. So you see in this image, these are all the filters that were present. So first, it looks for, this layer is looking for, where can I find an edge which is slightly diagonal, going from black to white, rather dark to light. The next layers then combine these features. Let's say if you combine a vertical with a horizontal at the bottom, you get sort of an L shape. So now you get more sophisticated features, and you keep moving on and combining those. Now the middle layers are detecting ears and noses and eyes and so on. The final layer looks like it's detecting different kinds of faces. Can you see them and say this looks like a male, this looks like a female?
in the finals, on the right, you mean? Or the pieces in the middle?
Yeah.
And then right. Top right.
Somewhat.
So
They all like look like dolphins that laugh when you turn the lights out.
like in the top row, the fourth column, the guy has a mustache. It's relatively easier. Bottom row, third column, seems like a female. So now if a given image comes in and it's similar to the top row and fourth column, it's easier to say, yeah, this high probability is a male. Okay. So let's try some new notebook that we have today. And then we'll go back to the last week's notebook after we've done this. This is a very nice explanation done by Luis Serrano. He also has a very good explanation on recurrent neural network using pizzas and burgers. So if you have images, let's say it's a 2 by 2, and you're just detecting backward slash and forward slash. So how can we do that? So the image, let's say one represents the red color, and let's say -1 represents gray. So the forward slash can be shown in this image and the backward slash in the lower image. And then the computer really reads these arrays of numbers. So if we go from left to right, first top, then bottom, this becomes 1, -1, -1, 1. So can we come up with a rule for these two arrays that a computer can apply so that we can categorize them as distinct images with high confidence? Can you think of a rule? What if we add them up? That didn't help. What if we multiply them? Same. What if we use this top left, whatever is, we'll take that as a plus, so it'll be +1. Top right will be a negative, so negative, negative, -1 will become 1. These green operations, if we apply, then what do we get?
I'm sorry, can you go through that sequence again? What are you saying you do?
So plus means we take +1, minus means we take minus of -1. Now it's +1, +1, and then we do the same on the second row, first column, which is minus of -1, and second row, second column, which is +1. What do we get? This is the operation.
So you assign meaning to the pixels. Like if you positive, negative.
They already have a value, you're operating on the value inside it.
Right.
Yeah.
But that operator itself is just applying a type of meaning.
In a sense, I don't know how to interpret the word meaning, but yeah, we are applying a pattern, a fixed pattern on top of that image. And we are seeing if we apply that fixed pattern on top of the image, what's the output? So if we apply this pattern, does that work?
Does this time?
Okay.
It's different.
So this is essentially the pattern that we applied. We had what we call a filter. We can think of this as +1, -1, and -1 and +1. And then you multiplied this filter with the image. In one case, you got +4. In the other case, you got -4. And if you look at this filter and the one where it got +4, do you see some similarity? This guy and this guy.
They're essentially the same picture.
Exactly. Essentially, it's saying, the filter itself is a /, sorry, this is a /. And it's saying, can I find you there?
So a filter, rather than looking to exclude something, is really like a mask you're trying to find.
Very good. So we'll talk more about that. That's exactly what we're doing. So how does that rule work here?
Different answer. But no.
So can we think of the top one as a /, but probably not the cleanest /.
Yeah, kind of looks like that.
Right. And the bottom one, can you think of it sort of as a /?
Yeah, if these pixels were next to other pixels, this could be the ending of a larger / or something.
Right. So it's showing that there's some level of robustness in this process. The key thing here is, where do you set the threshold? Do you set it at, let's say, 1.5? In this case, this will be called a /. Or do you set it at 3, in which case this won't be called a /. So the threshold is a very important concept. So now the question is, how do we figure out this rule? So if we just have 4 pixels and we just have 2 options for each, and 2 to the power 4 is? Okay. 2 to the power 10?
1,000的番茄多。
Very good. So
2 to the power of 126.
The square root of that, please.
So, who's the CEO of Facebook?
I'm sorry, what?
Who's the CEO of Facebook?
Zuckerberg.
So he was giving a talk, and in that talk, it came up 2 to the power 10, and he instantly answered 1026, and everybody was clapping. Anyway, so here we have just 16 choices, so the computer can enumerate all of them and figure out which ones work. So small question, is the number of all integers larger than the number of all real numbers?
Intuitively, I would
Yes.
think no.
No, and you said yes.
Yeah.
Infinite is infinite, but I would think you can squeeze in more infinite with all reals. I don't know, I'm not a mathematician. I only apply 1.5 to my filter.
Unless I'm getting this wrong, isn't disregard.
So 4 of our greatest mathematicians tried to prove that infinite number of real numbers is larger than infinite number of integers. And they ended up killing themselves eventually. But never solved the problem.
So you asked us this question because you hate us, is that right?
You wanted to start a new class, okay. On the ashes of the old one.
I asked this question to ensure that we don't go on that path. The point is, number of real number represents everything in the universe. Number of integers are sort of theories to explain everything in the universe.
They're what to explain?
Theories to explain everything in the universe. So you can never have enough theories to explain everything in the real universe. If you think of between every 2 integers, there's an infinite number of real numbers. At an intuitive level, for a mathematical proof, apparently we don't have that. So if we just have 4 numbers with 2 options, we have 16 choices. But if we have these as real numbers, we have infinite number of choices. So even the computer can't simulate that. If it is just 16, let's say it starts with all 4 positives, and it changes one of them, converts that into a negative, and one of them works better. So then whatever works better, it keeps that and creates some other versions of it, makes some other changes, and it picks a better one. So at each step, it is making a change that's improving the situation. This is if we have only 4 numbers. But this is real numbers where we have infinite number of real numbers. So how do we figure out the right matrix that will classify our images correctly?
Can you make them kind of have gravity or rounding or
Bingo.
sticky?
Gravity is the right answer. So let's say you are in a mountain area and your job is to find the lowest point in the valley. And you have a small torch, and all that can help you do, it has very little light, so it only just show you your surroundings, few feet. So what will you do to find that bottom of the valley?
I guess like calculus trying to find the local minimum. Is that right?
Right.
You won't know if there's a deeper one somewhere unless you take that lowest point and then keep that in mind and then go searching and see if you drop off somewhere.
So how do you figure out what's the next step?
Whichever one goes towards sloping down.
Very good. And let's say you found a bottom. As you said, it may not be the bottom for the whole valley.
Because it might be rippled.
Very good. So what can we do to increase the probability of finding the bottom of the whole valley?
First, I would try to scan across like some equidistant sections, some small number that I could handle, like maybe 100 equidistant points, and say which one of those is lowest. And then if one of them is lower than all the other points, then I would start there. But then maybe it would make sense to, after picking that point, to then pick twice as many points and see if that changes what your lowest number is. So I think kind of divide and conquer, trying to find your lowest points.
Precisely. So you can think of randomly starting at various points in the valley. And from all those places, you start walking and finding the lowest point. And then amongst, let's say you did 1,000 walks, among your 1,000 walks, you find which is the lowest point. And that's the bottom that you found. There's no guarantee, but seems fairly reasonable. If you did a good job of picking random points, with a reasonable probability you found a good solution.
So question, I'm not a mathematician. Mathematicians I've talked to always seem to like random, whether it's an algorithm or whatever. You start with this random point for your pivot or something.
That's how our life is.
Why
Wake
not
up in the
choose-
morning, do something random.
So how do you know that your random doesn't predispose you to one section?
We don't know. That's a very good point. So there's something called stratified sampling,
Okay.
which is exactly what you were saying. You sort of break the whole space, let's say into rows and columns. And within each row and column, you randomly pick a point. So now you're ensuring that you're randomly spread out throughout the area. That's a very good part. So this process of looking with a torchlight, with a spotlight, around your neighborhood and taking that one step, what is that called?
Gradient descent.
Very good.
And if you're drunk, it's called stochastic gradient descent.
That just depends if the lady at the party you're talking to is really cute.
So what's the difference between gradient and stochastic?
Stochastic has doesn't have consistent step size. So sometimes it'll take a larger step, say it can find, so that it can ensure that it hasn't fallen into a local minimum.
Oh, because if you had like a totally periodic, like sine wave or something,
Yeah.
you might choose a point that's going to be the same on all of them. Is that right?
It's possible, but
Is that what this guards against?
the idea is that if you have, let's say you have a slope like that, and then there's the actual canyon over it. If you're going down the mountain in regular steps, it's going to come, because of how the operation works, once it hits a flat point, it goes ding. Because at each point, it's measuring location and slope, and it's following the
So
slope.
this is gradient.
Yeah, so
Stochastic.
stochastic has kind of almost randomization in step size. So it may get to that point, but it's more likely to overstep a local minimum and come into any location. Yeah, because when you're looking at in high dimensional space, you're going to have kind of rippling. I'm trying to think of the best way to describe it.
Yeah.
Okay, I just want to add a few things. So
Okay.
now we just talked about the effect of stochastic gradient descent. So what you will get is some of the randomized procedure to get this guess the global minimum, but local minimum. Well, depending on whether your function is convex or not, whatever. So how do we get this? So I want to talk about the approach, the exact approach. So with gradient descent, every time you calculate the slope, the direction, you use the whole training data set, if I remember correctly. And with stochastic gradient descent, because we want to reduce the time spent on calculating this slope, calculating this gradient. Anyway, when it's reduce the time, so every time we only take a subset of the whole training data set. So in the extreme case, we will only take one data point. And in other cases, we will take a batch. So that's why we will get this weird randomized behavior when we're going down the slope, because we are not taking account into the whole data set every time.
So it takes less calculating.
Yeah.
Okay, I didn't know that piece to it. Thank you.
And every time you take a step in regular gradient descent, are you guaranteed to have an improvement, or at least that you won't get worse?
No.
Regular gradient descent.
Yeah.
Oh, well, if your target function is convex, then yes.
Right. And how about stochastic?
Well, if you're only looking at a subset of your training point, then the gradient calculated may not be the best gradient for the whole training.
Very good. Do you guys get the point?
Roughly.
Okay.
I guess I'd say like if whatever you're searching has like dimples on it, if you're only looking like what's the lowest point around me, it's like, oh, it's that dimple, and you get stuck there. Like you need to think.
So with stochastic, though, I thought the point was it helped you not get stuck there.
Yeah. Kind of take a bigger step. Probably.
But you can still get stuck there.
You can still
you
get
got
stuck in
unlucky,
a local minimum. It can happen. It's just a method to avoid it.
Okay.
Well, so whether you will be stuck in the local minimum, or whether you can always get to the global minimum, depending on the shape of your loss function. So depending on the target of your optimization. If your target optimization is convex, like strictly like this, you will always get to the global minimum bit. But if your target is something like this, you may be stuck in the local minimum.
And especially as you get to higher and higher dimensional spaces, you're unlikely to find a convex function.
This is just like people who get depressed or something because they can't see that their future is going to be great. And you're stuck in this little depression.
Yes,
and they
that's a
can't see the
glorious way of
future.
seeing it.
Yeah.
Yeah.
Gotcha.
And then Google has, and I'm trying to remember what it's called, they have a specific gradient descent function that has a randomization in it that causes it to take a step that doesn't have a basis in anything sensible. So it's likely to keep it from sticking inside a local minimum. I'm trying to remember what it's called though.
Okay, the way you do this in management is management by walking around. And even though you think you know what's going on, you can go check around the other territories. I just didn't know there was a name for it.
Yeah, so as Jackie mentioned, so let's say you have a bunch of valleys and regular gradient descent. It looks at all the data. So for all the data, you're going to improve a little bit at every step. So if you're sort of in a local valley, then you're likely to go better and better and get stuck in that valley. In stochastic, what can happen is the stochastic, let's say you had 32 data points. And for those 32 data points, the error improved when you take one step. But you had 1,000,000 points. If you take all 1,000,000, you actually move to the next valley. It's possible that that next valley is deeper. So that allowed you to escape that local minimum. So that's where it can help. But everything is productionized in deep learning to have all the training and all the inference done in batches. So what is the serving platform from Google for deep learning?
AutoML. Oh, I'm thinking of something else. Never mind.
Okay.
Those starts with a B. Bird?
No.
No.
So TensorFlow serving.
Oh, okay.
So they specifically built it for deep learning models. And it's extremely fast, and it uses sort of batches of data for training and also for inference. You can actually tell it to wait until you have the whole batch in the configuration. And once the whole batch is ready, then it will do the inference. There's another framework that Facebook has come up with, and Microsoft and AWS joined them. Facebook and Microsoft tried it on 60 of their models, and it increased their efficiency 3 times. That one is called ONNX, Open Neural Network, I think, Exchange. That is the rival for TensorFlow serving. At some point in time, I'm hoping that all of us sort of build models and deploy them. That's why I'm sharing. So then apart from Facebook and Amazon and Microsoft, NVIDIA and Intel have also joined. So they provide hardware accelerators. Baidu has joined. So Baidu had its own framework called Paddle. So now you can convert that into ONNX. So those are the 2 main frameworks, and everything sort of works in batches.
What is the basic description of inference?
So once you have a model that has learned all the weights, now you have a new image, and using that model, you want to answer the question, is this a male or a female? So when you run that image through the model and get an answer, that's an inference.
It's that last comparison of this image is the inference. Infer
Yeah.
it is or it isn't.
Yeah, exactly. You have your data point, the model looks at the data point and gives you an answer. That's it. Okay.
And the gradient descent here is to try to find a filter. That's how we end up on the gradient descent.
Right. So these filters are weights that we have to learn and learn them in such a way that they sort of minimize the errors. So that's where gradient descent comes in.
Because we cannot try all the possible values.
Precisely. It's infeasible.
So how does this relate to gravity?
Because
Gradient descent.
just like you take steps and gravity sort of pulls you to the lowest point, in gradient descent also you take steps to minimize the error. So gravity minimizes the distance between you and the center of the earth, and gradient descent minimizes where the model is to sort of minimizes the error for the model on that data.
But it's doing it for each time it compares, for each time it does a mask, or is it for each one of these numbers?
Yeah, it changes each one of these numbers. For each number, it asks the question, if I increase it, will the error get worse? In that case, I should decrease it. And then the question is how much? For each of these numbers, it asks those questions and adds on. That was for forward slash and backward slash. What about if we have an X and an O in there? How can the computer solve this problem?
We can look for things like vertical lines, curves,
Very good.
things on the outer edge.
Very good.
Can we check to see if something's like mutually exclusive?
Right, like building up from the forward slashes.
Yeah.
From the slashes.
Very good. Yeah. In some sense, yes. Certain things, like if you break this down into forward slashes and backward slashes, like the previous examples, some of them will be present in one, let's say in the first one, but they won't be here, and vice versa. So there's some exclusion and inclusion. So these are now our building blocks. These are our filters. So the X, the O, a forward slash, and backward slash can be created by combinations of our two filters. Does that seem reasonable? So that's the job of the convolution part of a neural network. So most of the beginning is this convolution. Now let's think of how this works. Let's go here. So you have the first layer with a bunch of these. You have a bunch of filters in here. So they are sort of stacked one next to the other, like this.
Were these randomly created or?
No,
how
these
were
are
they
learned
learned?
by using gradient descent.
Okay,
So you have different kinds of edges, dark to bright, bright to dark, different angles, and so on. Now the next filter, what does it do? The next filter in the first and the second layer, what will it do?
In this case, it's like identifying the features like eyes and nose.
Yes, but the next filter has, if we have 40 of these filters in the
Yeah.
first layer,
Yeah.
in the second layer, the next filter also has 40 layers, and all of them do sort of a dot product on this layer. So each filter will do a dot product on each of the previous filters. So try and think about what's going on. Let's say you have, how many are these? These are 3 and 3, 6 and 4, 24. You have 24 of these, one after the other. That's your first row. Now your second row, first filter, also will have 24. And what that is doing is looking at various parts of this filter and saying, and sort of multiplying all those numbers and calculating them. So what exactly is that process doing?
I'm trying to see if I am confident about understanding what you said.
Yeah.
So you have 24 filters like that.
Yeah.
And then for that, are you saying that for that next?
Let's forget those for now.
Oh, okay.
Let's forget the other layers. Let's just think of the second imaginary layer in our mind. All we know is that each layer will build a combination of the first layer filters. So now your job is to come up with a filter that's looking for, let's say, an L shape, which really is a combination of two of these. So how does it do that?
The first filter, let's say it's vertical line, right? It's gonna tell me, okay, here's everywhere in your picture where you have vertical lines. That's like one of my layers. That's equal. And then
Say that again. That was very good.
so the first one, now I have like this thing that tells me everywhere where I have vertical lines, right?
Very
And then
good.
I go to the next one and it tells me everywhere where there's horizontal lines.
Very
And
good.
that's great, but I need to somehow like
Very
know
good.
where there's a horizontal one next to a vertical one.
Very good.
I mean, I'd almost imagine like collapsing it all, getting taken the highest, most likely one out of all 24 layers. So I kind of have like it. So now on each square, I have a value between 1 and 24 or something. Which of these 24 different features is here?
So wouldn't you need another layer to say that the horizontal line matches at the bottom of the vertical line and it actually is to the right of
Yeah,
it?
that would be nice, right? Yeah, it's like if I have a 2 and a 4, I know that's way up now or something. Right?
Very good. So, yeah, when we have an image and we have 24 of these, go look at all over the image. The first one says, do I have the slanted line going from dark to white? So it goes all over and it generates something. It says, here I found at this spatial location, I found a slanted line, and here and here. The other filter, let's say, is looking for a horizontal line. That also went all over the place, and it said, here I found it, this line, which was horizontal, and let's say here and here and here. So all these filters have now created these 24 new images, sort of, which are saying here and here and here I found the slanted line. Here, 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 here I found the horizontal line. All of them are saying this is where I found something like this and so on. So now you have these 24. Okay. In the next one, the filter is looking for an L shape. And it also has 24 channels. And it is saying, if I find, for the first filter which has these lines, if I find that, and relative to that, if I find in this location, for this filter which looks for horizontal lines, as long as those two are there, I know this is an L, and all the other things are zeros.
Even if it's just close, because there's several versions of horizontal that for a letter L would kind of do.
Right. So in that case, I'm just simplifying things. But there could be multiple matches. But to simplify that, if you just find it here, and for this one over here, now this filter is saying, I found these two guys next to each other. I think this is an L. So now this filter is defining that L using those constituents of this and this. So if you look at those layers, they don't look like these. They are really telling you how to combine the previous ones. So, but they represent these. In the image, they're looking for these patterns. But the weights, if you just take all those matrices and try to look at them, they'll just look very random. So that is, in a sense, how the whole network is working. Take your time, think about it.
So not everything in an image has to do just with edges, right? There's also like the intensity of something or the color of something. Do most image processing systems just look for edges?
In the beginning, they look at things as fundamental as that. Now, this can encode intensity. So these are black and whites, but even in black and white, it's looking for numbers between 0 and 1, where 0 is black and 1 is white. That does have the concept of intensity, 1 being the most intense and 0 being intensely black. That concept is there.
So if you have a broad range of interesting intensities, you could make it learn that as well.
Yes.
I have a question. Can we go back to that alley example?
Uh-huh.
So let's just say in the first layer, we have a feature map constructed for, let's say, vertical lines, and another feature map constructed for horizontal lines.
Mhm.
My understanding is that in the next layer, we will somehow have a feature, no, was it? Oh, it's a filter map, not feature map, what I said. Filter, a new filter that somehow can find this L pattern. And what we do is that we also apply this second layer filter in a scroll manner to the first filter map, and then to the second filter map, and then do we add them up, or how do we get the?
So whatever is there in the second layer,
Mhm.
we will convolve that throughout
Combo.
for each of the previous filters.
Mhm.
So if we have a vertical line, so if there are two of those,
Mhm.
then the next, each filter will have two channels.
Yeah.
And in the first channel, this thing will convolve throughout the place. And the second channel will convolve with the second one.
Well, let's say the second layer has 4 filters. After I apply this after apply all the 4 filters to the first layer, I should get a 4-dimensional matrix, right?
Correct.
But then how do I combine the 2 channels of this filter? I still don't quite get it. So I do not just add them up?
You do.
I just add them up?
Yeah.
Okay, so yeah, this is a little weird. I'm just thinking what kind of shape this filter needs to be to identify a vertical line in the first filter map and a horizontal line in the second map, and somehow after I add them together, the number here is a large value.
All right. So let's say it has your second filter, L shape, has 2 channels. So for the channel related to the first vertical line, let's say it has a vertical line, and for the channel related to the horizontal line, let's say it has a horizontal line, but at the lower level. So let's say the first column, let's say it's a 3 by 3, and the first column, first 2 rows is a straight line, and the last row, last 2 columns is a horizontal line.
Mm-hmm.
So here it will find what this guy looks like, a vertical. Here it will find this thing looks like. And then it has to sort of collapse them and add them up.
Okay. I mean, the filter itself will basically look like an L shape. Will it?
In the multi-dimensional space.
In the one, but the filter is a 1-dimensional filter.
Is it? I mean, you have to look at both layers at the same time, or you'll never find the L, right?
Yeah. I mean, the filter is. The
You see,
filter
that's why I
map
need
is
to improve my
multi-dimensional.
linear algebra, right?
This is just being an artist.
Mm.
You're just thinking about art. You're imagining things.
I wonder, like, because in the picture, it shows like the pictures of the eyes on the second layer on there. And like on the first picture, it's like a mask where it's like, okay, it really is doing what it looks like. It looks for something like this, and you get that score, right? But in the second picture, kind of based on what he's describing, it's like here's what the type of things it finds, but this is not really what the mask actually looks like, right? Because you can't even really visualize it because you're looking at 24 layers at the same time, which is like a large number. So if I were to try to like do an analogy for myself to simplify it, I'd almost think of like maybe color photography, right? Because they will kind of sample the same scene in 3 different layers, right? Like 3 different colors, right? Like RGB or whatever, right? So if you wanted to find the orange ones, you'd have to see where the red, and the yellow overlap, right? But if you look at any single one at the same time, you'll never find orange or something. I don't know.
I just wanna say that when we say the filter learns how to combine these channels together, it actually doesn't learn how to combine them together because actually each channel is assigned the same weight when we add them together in the last step. Yeah. So basically, what we do is the same as adding this together first and then apply this filter.
So the numbers that are there in your filter, in the second layer, those numbers can be high or those numbers can be low. So is that a way of providing weight to different filter, to different previous layer channels?
To different channels? Another question. So do we apply max pooling for each channel or do we apply max pooling after we combine after we combine the channels? Yeah. Then my intuition is that if I apply the filter to each channel and then add them up, the result will be the same as if I add them up first and then apply this filter.
Sorry, say that again.
Oh no. Yeah. Yes or no? I was not clear what I
So
said.
I think what you're asking is, if you basically didn't have that filter, you simply added up all of the layers that you know are associated, you would come up with a number. The same as if you
I will add up all the channels and I will get a combined channel and I apply this filter in the convolution.
So is the filter more like, almost like a, I don't know the right word, I want to say data set, but that's not what I mean. Almost like a compressed meaning that it represents a set of those. And then you take that set and you can apply it to other things besides just this particular, no, I'm getting lost. I'm sorry.
So the key difference is in one, you're adding them up. In the other, you're doing a weighted mean. You're giving different weights to different previous layer filters.
Where is this weight from?
Because the second layer that you have, which has, in this case, 2 channels, those are numbers.
Yeah.
So now those numbers are between 0 and 1. So let's say in one channel, the weights are close to 0.9s. Let's say there's a third channel which sort of had a slightly slanted one. So there it can have a weight of 0.7s. So in that sense, it is providing weights to different filters and then adding them up. And once it adds them up and it looks good, then it does the pooling. If that pooling is max pooling, then it's basically picking the biggest numbers.
Oh, okay, I see what you mean. But the 2 approaches I described are still essentially the same. Because finally you add those weights up, it's basically like whether you do ax plus bx or a plus b times x. That's the only difference.
I haven't understood the question.
Well, so,
Are you saying max pooling
not,
at each layer or max pooling at the end? That's the difference?
well, did we just,
So X
agree
is
that
not-
max pooling
X is
done
not
after?
same.
X is the filter.
It's AX1 plus BX2.
Y-X is not the same, X is the same filter.
No. So if you have two channels,
Mm-hmm.
the next filter also has two channels and they can have separate weights in them.
Oh, the next filter will have two channels, but,
And it will have separate weights. The weights are not same.
Okay, but from the TensorFlow code, every time we just, so the next, for example, if I, in the TensorFlow code, I say in this layer, I want 16 filter, next, each filter will have like a variable number of channels depending on how many filters I had in the last layer.
Let me show you something.
Oh,
So it's not-
okay, I see that. Yeah. So basically, even if I say I have 16 filters, essentially I may actually have 32 or like more than that. I mean, if I say I have 16 filters, essentially I can have more than that number of matrices.
So each filter
because
can
each
have multiple
filter can have
dimensions, is that the key?
Multiple channels. Is that the reason why
So same kernel, but 3 channels. And it has different numbers for each channel.
No, sorry, thank you. It's a big yellow.
So we have the same kernel and it has 3 channels. There's the original image of red, green, and blue. It has different numbers in the channel. It's a weighted sum. It gives different weights to different channels.
okay. Two different channels. So is what I said correct? Like the number of filters in the second layer actually depends on the number of filters on the last layer. I mean because if a filter can consist of several channel filters. Let's say if the first layer has 2 channels, and then say when I say I will have 4 patterns, I want to detect the 4 patterns in the second layer.
So now
then,
we have 4 filters
4 filters.
and each of them will have 2 channels.
Yeah. Oh, okay, I see. So that's essentially 8 matrices then. Oh.
And each of those can have different numbers.
Okay, that's where the confusion is.
That's a very good point. And it's only this place that I found that showed it very clearly. Most places don't clarify that thing.
Oh,
I'll send you this paper. Okay. Do you guys want to take 5-minute break or should we continue?
We can take 5 because Terry just stepped out.
Okay. So let me pause the recording. Something you want to share?
It was the, you know. Yeah, better than gesticulating in the air.
Right. Yeah, somehow I enjoy gesticulating in the air. It reminds you everything is imaginary, rather temporary. So, yeah, so what we just discussed, that was what the convolution layers are doing. And once we have all those, then as an image goes through in the first layer, let's say it activates some edges. And because of those edges being activated, some forms of combinations of those edges form, let's say, different corners in the second one. Some of them get activated. And that then leads to activation in the next few layers. So at the end of the convolution layers, we'll basically have some filters that are sort of more activated than others. That information, we then run it through a regular feed-forward neural network to make the final decision whether, in this case, it's an X or an O and stuff like that. So the first few layers have those feature combinations, and the last layer essentially provides different weights to the various features to make a decision as to what kind of object this is. So let's see a bit more closely how that works. Sorry, is there something you wanted to discuss?
No, sorry.
Okay. So we have this backward slash feature, and we run this. So we take this and we put it here. So what do we get? Right, we get 4. And similarly, we take this feature and put it here. What do we get? And we put it here, we get -4. We put it here, we get +4. So then we apply pooling.
Let's take our thing out there.
So essentially there are two kinds of pooling. The more popular one that's used more recent times is called max pooling. So basically look at a bunch of numbers and pick out the max number from there. So essentially the convolution layer is saying, did I find my pattern? Did I find my pattern? Did I find my pattern? How much? What's the weight? What's the probability that I found my pattern? And it says, well, amongst these guys, I'm going to pick the highest number. So this is where it really found the pattern, and these are just neighbors. That's our pooling. So it drops the -4s and the -4s, and it keeps these 4. So we have one backward slash here and one backward slash here. So that's the process of convolution and pooling. And now you have identified these two kinds of features.
So by pooling, you mean you're pooling what you think had, value and discarding the others?
Essentially. So this shows pooling.
Read a lot faster than I do.
Yeah. So this is pooling. Can somebody explain what pooling is? I'll just knock on my friend's door.
So it's like you're just from each space pulling the max number and you're aggregating those into some other space.
Yeah.
Okay,
So it's like a summary of the overall.
precisely. Very good. Okay. So once we have done that, next step is combining them. This is sort of as the next layer feature, combining the previous layer features. In this case, it gave them equal weight. So now once we have combined the features from the previous layer, we get this new feature. And so that was for the case of X.
Well, is the combination done before or after max pooling?
After, because this is the next layer
After,
that's doing.
after max pooling combination.
Concatenation.
Combine different feature maps. Combine.
Yeah.
Well, why do I need to? Oh, you mean this is right before the fully connected neural network?
Yeah.
Oh, yeah. I see.
Okay. So this is for the O's, and this is the combinations of what we found. Essentially found that, these were present here, these were present here. And these were the locations relative to each other where they were present. And if we sort of combine them, then we get this. So the next, and this is for the other ones. So essentially, this is for the forward slash. So let's look at it here. So what we have done is we have said that if you're looking for the backward slash, then we found it in this location, we didn't find it here, we didn't find it here, and we found it here. If we are looking for the forward slash, we didn't find it here, we found it here, we found it here, we didn't find it here.
Is this what you were calling a feature map?
Feature map is basically after you apply this feature, not a feature map, what I just correcting myself, it's a filter map.
Oh,
Yeah, it's just after you apply this filter in a convolutional way, what you get as a result.
so what do you call that center mapping that you have?
Sorry?
So where you were saying that where you have that positional map of where those features are found, what do you call that set of things?
So that's one filter.
It's a filter, okay.
Yeah. So what we're looking at is just this. we found the backward slash at position 1. We didn't find it here. We didn't find it here. We found it here. So 1, -1, -1, 1. Same thing here. -1, 1, 1, and -1. So essentially we can represent these images as the presence and absence of these features. This is what the convolution part does. What the next layer, which is the dense feed-forward neural network layer, does is, it says if you have a pattern like this, it means an X. If you have a pattern like this, it means an O, and so on. So it applies these 4 patterns, which it has learned for 4 different categories, and gets the highest score here for an X.
So the middle filter, those may not always be ones, negative ones, they could be other numbers. But you're saying that whether it's a positive or negative value is the only thing that you're mapping in that third layer? Filtering in your third layer?
So essentially what it's saying is, instead of a positive number, positive sign, you can think of it as a high positive number. Because we are going to multiply this thing here we are going to multiply this with this and this with this and this with this. Essentially, all of these numbers on this plus minus matrix will be multiplied by all the numbers on the left hand side coming from the convolution layer. So the convolution layer is saying, I have found for each kind of a feature filter, I have found the presence or absence in these locations. And the dense layer is saying, in order to predict that this is a human face, I want you to find, this is the probability, I want you to find this feature here, and this is the probability I want you to find this feature here, and so on. So the convolution layer is saying, hey, I found these features, and this is my probability that I found these features in these locations. The dense layer is saying, if you found these features here with these probabilities, I'm going to say this is a human face.
Okay, oh, okay, all right.
If you found these others, I'm going to say it's a cat.
So this is more like your comparison pattern with whatever numbers you actually can.
Precisely.
Okay.
So, yeah, that's exactly what's going
But
on.
these would have only operations, or would these have numbers and weights?
In reality, they will have numbers.
Okay,
So higher the number means higher the weight.
okay, okay. I was being too literal, that's why it was confusing me, sorry.
So thanks for asking that. So in the real world, yeah, all these will be real numbers. But this is sort of the gist of what the network does.
So if it gets an answer that it's not very sure about, can it go back and try again?
So what it's going to do is, it's going to apply whatever ends up from the convolution there, it's going to apply these four matrices.
Totally deterministic.
Yeah, those weights are set. And that is going to give it different scores. And based on the scores, it can give you the probability that, so let's say here it's very clear you got 8 and the others are -4 and -8. But let's say you had an 8 and the others were all 7.5. Now the probability is more diversified. You can't be that certain that it's just this. But in this case, it's either an 8 or -8 and -4 and so on. The probability is larger. So that, yeah, essentially that is the gist of what's going on here.
And is it generally just like those 2 layers?
Sorry?
Is there ever like more layers, or is it generally just these 2?
Yes. So what we didn't cover today, which we will next time, are these different models. So LearnNet was from Jan LeCun. It was created for recognizing digits. It had about 60,000 parameters. So we can see first is convolution, then pooling, then convolution, then pooling. And then these feed-forward neural networks where it has learned those weights. So this was 60,000 parameters in 98. AlexNet came, and this had average pooling and not max. And then AlexNet had 50 million, something like that, parameters. And then we have VGG, which had 150 million parameters. So this was in 2015.
Parameters, you mean like just numbers to evaluate things?
Right. So each filter, let's say it has 10 channels, then all the numbers in there for each channel, it has to learn those. Now, what's interesting is that because the same filter is run on the entire previous whatever image we have, the number of parameters in it are limited. The real parameter growth comes from the dense layer, because that's n by n for all of them. So most of the parameters come from the dense layers. So this is 138 million parameters. So can you guess what's the largest deep learning model that came out last 2 months? How many parameters?
17 trillion.
I don't think it'll make any sense of this, but let's see. Okay, we broke the transformer.
Oh, okay.
Two.
Okay. How would regular English statement? Anybody? Okay, this is horrible.
I want to wish you a merry.
But is this sort of like,
Then it's gonna link to a Patreon.
you, but or you're supposed to go to Shakespeare.
It's not supposed to. Okay. Not too horrible. So this has 1.5 billion parameters.
And that's all it can do. Why are we learning this crap?
How many parameters is it?
1.5 billion.
Oh.
Okay, so that was our class for today.
Thank you.
Thank you.